Our next speaker is Dr. Christiane Auray Blais, Director of the Quebec Provincial Mass Urinary Screening Program in Quebec, Canada.
So I'd like to thank Oslam for giving me the opportunity to present our work in Sherbrooke and to attend this great meeting. So this is my disclosure slide. My topic is quite different from the rest of the presentators, the speakers. I've been working in mass spectrometry. So mass spectrometry, I don't know if some of you are watching the TV program CSI. In CSI, they have mass spectrometers, they inject a sample, and about 5 minutes later, they have the face of the criminal. So it's really not like that, and I'll show you why, doing metabolomics. And so we do biomarker discovery. We devise methods in order to do technological transfer to clinic. So we want to detect patients, high-risk screening. It can also be mass screening. We want to diagnose patients, monitor them, and offer a follow-up of these patients by looking at biomarkers. So today I'm going to talk about Fabry disease and also mucopolysaccharidosis and the test that we've devised for both of these lysosomal storage disorders. So for those who are less familiar with Fabry disease, it's an X-linked lysosomal storage disorder. Men are affected, but women can be affected and sometimes as severely as men. It's due to alpha-galactosidase deficiency. There's over 600 mutations, so great variability in the genotype and phenotype. It leads to storage of glycosphingolipids, so mainly GB3, lyso-GB3, and some of the analogs that we've detected, so the analogs of lyso-GB3. So there's accumulation in biological fluids, organs like kidneys, heart, eyes, vascular endothelium. It may present early in childhood or later on in early adolescence, and it can lead to early death due to ventricular hypertrophy, CNS complications, renal insufficiency. Patients present acroparesthesia, angiokeratoma. So it's quite there's a great variability in the phenotypic aspect. So it has been published that it might take 14 years to detect a man with Fabry disease. So he goes from one doctor to the other without knowing that he has Fabry disease, and 16 years in women. So these are the biomarkers. On the first part, it's GB3, which is comprised of 2-galactose, a glucose, a sphingosine, and different chain lengths of fatty acid. So that's what we analyze, isoforms of fatty acid. Whereas lyso-GB3, it's a molecule quite similar, again, comprised of 2-galactose, a glucose, but it's a deacylated molecule, so there's no fatty acid. So, what is metabolomics? It's really the identification and quantification of all metabolites, so less than 1,500 Daltons in a biological system. So we can analyze urine sample, plasma sample, CSF. We can extract biomarkers from tissues. We've been working with mice, so all the possibilities are there. And what we call metabolic fingerprinting is, in fact, when we perform metabolomics, we look at patients having a disease and controls, same age, same sex, and we try to find differences by doing multivariate analysis. So that's what I'll be showing you in a few minutes. The purpose of doing metabolomics is really to understand the biochemistry of diseases. We want to discover biomarkers that could be useful for patients. And whenever you discover biomarkers, you have to elucidate the structure. So then we do tandem mass spectrometry to characterize the molecules. So this is a QTOF, ultra-performance liquid chromatography. So we do UPLC and a quadrupole time of flight. The principle is very simple. When we do mass spectrometry, we look at ions, charged molecule. If the molecules cannot be charged, we cannot do mass spectrometry. So we are looking at masses. When the masses are higher, that are high masses, they go slowly in the QTOF. When they are small masses, they go more rapidly. So we can separate, due to their retention time and their masses, we can separate metabolites. So we've published this paper in Analytical Chemistry in 2012, where we found biomarkers for lyso-Gb3, so the molecule which is a deacylated molecule. So what we did targeted metabolomics. So we looked at amines, basic molecules. So we perform a solid phase extraction procedure. And so amines means looking at amino acids, purine, pyrimidines, sphingosine, phosphatidylcholine. So looking at a variety of molecules. And then we treat data doing a multivariate analysis. Usually it's orthogonal partial least square discriminant analysis. This is done by the software. So just to show you a technical aspect of the software EasyInfo that was used, you can see that if we fix the threshold on the mass spectrometer at 5 for the peak area, we looked at controls and Fabry patients, we detected 50,000 biomarkers. If we fixed the threshold at 10, we detected almost 16,000 biomarkers. So we decided, let's fix the threshold at 50, and we'll see what comes out of that. At 5, I mean, and look at 50,000 biomarkers. So to do this study, 63 Fabry patients were evaluated. So 18, well, they're all untreated. You can imagine that we never work in metabolomics with treated patients because treated patients have low levels of biomarkers. What we want to see is patients excreting high levels of biomarkers. So they were all untreated. 18 were males, 45 were females. And in controls, there were 59 controls. So what you see there is a score plot. So patients are in red and in blue are controls. So 63 Fabry patients and 59 controls. As you can see with this multivariate analysis, we can separate those two groups. That means that there are biomarkers in Fabry patients which are not present in controls. We did the same thing for untreated female Fabry patients and female controls. Again, good separation between the two groups, and the same thing for male Fabry patient and male controls. But we decided, we detected some biomarkers, but we decided let's look at those patients who excrete very high quantities of biomarkers of GB3 and lyso-Gb3. So then we came out with only 11 untreated Fabry males and 23 healthy controls. As you can see, they're well separated, differentiated again. And it is in these 11 patients that we really discovered these analogs of lyso-Gb3. When I say analogs, it's because there's a modification on the sphingosine moiety of lyso-Gb3. When we talk about isoforms, it's modification on the fatty acid chain. So you can see here, every little dot is a marker, but it's not necessarily good biomarkers. So in the middle, you can see that there's a lot of biomarkers all clogged up together. They're probably amino acids, phosphatidylcholine, but on the upper right corner, you can see where the biomarkers of interest were. So these analogs of lyso-Gb3. So like I said, it's nice to detect biomarkers, but you have to elucidate the structures. What are they? So then we perform tandem mass spectrometry. And if you look at the bottom part, you will see the spectrum of the lyso-Gb3 at -2. So we call that lyso-Gb3. And then you see there's a loss of a galactose, another galactose, a glucose, and the sphingosine. So all these little peaks give us a profile, the structure of the molecule, which is of interest. So we did that for all the biomarkers, and we came out in plasma and as well as in urine. Whoops. We came out with the theoretical mass, the proposed modification, the delta mass, and the retention time. So we are sure of these biomarkers. We are sure that they are modification on the sphingosine moiety, but then it's important to quantify them. So then my master's degree student, Pamela Lavoie, devised a method to quantify all these 7 biomarkers using tandem mass spectrometry. So you have the structure of these biomarkers. Lyso-Gb3 is on the left side. And on the bottom part of the right side, this is the internal standard. We synthesize an internal standard because when you do mass spectrometry, it's important not to have suppression of ionization or enhancement of ionization. You need an internal standard to remove these matrix effects. So when we did the quantification, we found pretty interesting results. In fact, everybody was looking at lyso-Gb3. Ernst had published that in 2008 in PNAS about lyso-Gb3 in plasma, and we wanted to look in urine. We published that in urine, and we found that lyso-Gb3, if you look at this pie chart, is only 2% of urine samples of all patients. There's 164 Fabry patients. So it's like people were looking at the tip of the iceberg because lyso-Gb3 is such in small quantity. But look at the rest of the analogs. Some of the masses at plus 16, plus 34, plus 50, they're really in great amount in urine samples of Fabry patients. So then we've decided to look the effect of ERT treatment in a male Fabry child. So the child was 13 years old. You can see the different colors of the analogs, which were quite increased. And lyso-Gb3 is the first little peak, which is very, very small in the beginning of all these columns. And then if you look at 15 years of age, the child, after receiving ERT, all the analogs are lowered. And then there's the high masses, as I've mentioned. Again, they are still very increased in this child. Then if we look at ERT in adults, so these two adults, a 35-year-old female and the same for male, they had the same mutation. So you have before ERT, and then you have after ERT. And as you can see in the female on the right side of the x-axis, you can see that some of the analogs are still increased after ERT. But then, if you look on the bottom part for the male, all the analogs are lowered, a bit like the teenager. So again, different profile between men and women. And then you have the high masses again that are still there in great quantity. Then we've looked at patients having cardiac variant mutation. In type A, there's 1 in 1,600 the incidence of patients having cardiac variant mutation. They have an intronic mutation. They can really have serious problems. So then we said, what is the results? Because these patients, these cardiac variant patients, had normal Gb3. So if you wanted to detect them, you thought maybe this patient has Fabry disease. You sent a urine or plasma sample. It was normal for Gb3. And it was normal. As you can see, lyso-Gb3 is at 0 here for most of the children, and only in the adult who is 53 years old, there's a bit of lyso-Gb3. So again, if you just look at lyso and Gb3, you might miss patient. But if you look on the right side, you will see all the analogs. Some are increased and in very great quantity. So what we will do, I have a project with people in type A. We'll be looking at 234 samples from children, parents, and grandparents to better understand this complex intronic mutation and look at the biomarkers, look at lyso-Gb3 and the analogs. So people ask me, why shouldn't we analyze the analogs instead of looking at only lyso-Gb3? And it's true. When we do mass spectrometry, we can see all the masses together. So it's not a more complicated test to do all the analogs at the same time. So I think it's important to remember that these analogs can be very useful for certain patients having cardiac variant mutation, but also for other patients. They are biomarkers excreted in high quantities in biological fluids of Fabry patients. So then people always ask me, is there a link between Gb3 and lyso-Gb3? So we've published in Current Medicinal Chemistry in 2012 the relationship. So it's a big page with all the different fragmentations of the masses. So here you have methylated Gb3. So it's Gb3, but with a methyl group. So I'm showing the C22 methylation, but it's the same for C16 to C24 on the fatty acid chain. So on the bottom part, you will see that if they are methylated, where's the methyl group? Where is the CH3 group? So what we did fragmentation study again. So you have the spectrum on the bottom part of the slide. And as you can see, if we look at fatty acid plus the methylation, there's a mass at 354. And then we've looked at the sphingosine with the methyl group. We had a mass at that's 296, I think. So that means that the methylated group is really there and can only be there on the molecule of GB3. So then these GB3 isoforms, we've deducted, in fact, that these 7 methylated GB3 isoforms, there's a methylation going on, which gives GB3 methylated, and then there's a deacylation, which gives lyso-GB3. I was talking to Roscoe Brady a bit earlier, and you know, I've mentioned that to him, and he said, great. It's important to see the biochemistry of these biomarkers, what's going on in the body. Well, this gives us a fairly good idea for the relationship between the two molecules of GB3 and lyso-GB3. So in the end, people who are looking only at a urinary GB3 might miss patients. We've done a metabolomic study. I don't have time to talk to you about that, but we've done a metabolomic study with GB3, and we've detected 32 urinary GB3 isoforms, analogs. So in the body of Fabry patients, there are so many. The lyso-GB3 also analogs. So in the end, I think it's important to have a complete profile and to evaluate a complete profile of Fabry patients. And what we would like to do in Canada, we have the Canadian Fabry Disease Initiative, where there's more than 400 patients having Fabry disease, and they have been evaluated for since 2006. So what will be interesting is to look at correlation studies between all these biomarkers, and let's say for the lyso-GB3 patient samples, let's look at those patients who have cardiac problems, renal problems, or CNS involvement, and see if there are correlations with the biomarkers. So that'll be a very nice study to do. So in conclusion, the relative quantification of lyso-GB3 and the analogs really is important for detection, diagnosis, and monitoring patients, and particularly for patients having late onset cardiac variant mutations. And I've shown you the metabolic profile pathway between GB3 and lyso-GB3. I thought it was important, because the topic is really clinical practice and biomarkers, to talk to you about mucopolysaccharidosis and the work we've done in mass spectrometry for the analysis of different glycosaminoglycans, which I call GAGs. So the incidence of MPS 1, 2, and 6, which are treatable disorders, and some other disorders are, there's treatment in process. Also, there's a clinical trials for them, for MPS 4, and MPS 3. So if you look at the incidence, it's fairly rare, but all put together, there might be more patients also that are not detected, but they excrete dermatan sulfate and heparin sulfate in urine. There are tests for that in clinic, in biochemical genetics. These tests are spectrophotometric tests. They can lead to false positive, and they can lead to false negative. They are really not precise. So we thought, let's look at mass spectrometry and try to have a more precise analysis of these GAGs. So this is an MPS 1 patient, Hurler patient, really severe clinical manifestation. If you look at the clinical features, I was in Bahia, Brazil, to a meeting, and they really suffer. They have bone problems, dysmorphism, cardiomyopathy. So if we can detect these patients early, we can bring treatment, bone marrow transplant, ERT. There's possibility of gene therapy on the way, also being investigated. So since there's availability of therapeutic intervention, which can really alter the progression of disease and improve the clinical phenotype. And now with mass spectrometry, it's possible to look into that. So that's why we've been working with to devise methods for MPS and GAGs. So we've published in Molecular Genetics and Metabolism and Clinica Chimica Acta 2 papers. One was using liquid urine specimen. I will say liquid urine is liquid usually, but we've been working with urine collected on filter paper. And if you are there tomorrow, I'm going to show you the mass urine screening program where we receive urine samples from all the parents in Quebec for newborn babies. And it's so easy to send a sample in just a regular envelope by regular mail. So we've devised a method also using filter paper samples. So this is a filter paper under UV light. In urine, there are chromogene pigments that gives a whitish fluorescence, because it's important to know if you punch out a disc where the urine is. And often with babies, the urine sample can be diluted. So you can see very well where the urine is with the whitish fluorescence. And then I'm going to show, I won't go into details for the method, but this is an MPS 1 patient on the left side and an MPS 2 patient, so Hurler and then Hunter on the right side. And you can see before and after ERT, the lowering of all the gags. Years, I think it's like, it was about 3 years, 1 year before and about 3 years or 4 years after. So really gags stay low for both patients. So the objectives of the research project was really to look at the relationship between excretion of gags, disease severity, response to ERT, and the impact of comorbidities, including the development of antibodies to infused enzyme. So the next 3 slides are the same, so I'll show you this one more in detail. So this is the analysis of keratin sulfate, which is increased in a morchio patient. So we take this big molecule, this mucopolysaccharide, this big gag molecule, and we perform methanolysis with methanol HCl by heating for an hour. And then these molecules are then separated in smaller disaccharides. And this is what we analyze. So parent ions and daughter ions, so we have specific transitions. It's the same for dermatan sulfate and heparin sulfate. So these are the transitions that we're looking at. Again, as you will notice, we're working with internal standard. Very important to have the right value, not have suppression or enhancement of deionization. And this is the UPLC chromatography. So you have keratin sulfate, dermatan sulfate, and heparin sulfate, giving very nice peaks. And the linearity. Whenever we publish in mass spectrometry, it's very important to validate the method. When I mean validation is to look at the interday variation assays, intraday, look at the limit of detection, limit of quantification, linearity, stability. In Quebec, as you know, it can be quite cold. So the samples come, if they come on a filter paper by mail, it has to be stable. Molecules, they have to be stable on the filter paper. So you have very good linearity with a coefficient of regression, which is quite good for keratin sulfate, dermatan sulfate at 0.999, heparin sulfate the same. And then these results, they're all presented in the same way. So we'll look at, this is 3 MPS 1 patients. So on the x-axis, you have the values for keratin sulfate, dermatan sulfate, and heparin sulfate. So from these 3 patients, one had received bone marrow transplant. So it's the pink circle that you see down, so that dermatan sulfate and heparin sulfate is normal. But the other 2 patients, so orange and yellow, they have increased level of the dermatan sulfate and heparin sulfate. MPS 2, same excretion. So we cannot differentiate between MPS 1 and MPS 2 because they have the same profile for biomarker excretion. But they have clinical features which can be different. So when the physician sees these patients, it really helps with the clinical manifestations. So here we have one MPS 2 patient. It's the orange circle, which is increased in both dermatan and heparin sulfate. MPS 3, so San Filippo, heparin sulfate is increased in San Filippo. So we had 2 patients. As you can see, the 2 patients in pink and orange really show a very high increase of heparin sulfate. And then for MPS 4 patients, there were 6 patients that were evaluated, and 1 patient had received ERT, so it's the yellow circle. As you can see, dermatan sulfate and heparin sulfate is normal, and the keratin sulfate also is within the control, which is in green, but the rest of the MPS 4 patients all have keratin sulfate, which is highly increased. And the last one, there are 3 patients with MPS 6, Maroteau-Lamy syndrome. So 2 were treated, and they had low levels of dermatan sulfate. And as you can see, the patient in yellow had a high increase of dermatan sulfate. So we can discriminate by the analysis of all these gags, some of the MPS types. So in the end, doing UPLC tandem mass spectrometry, it's a multiplex method because we analyze them all at the same time. Well, it can be useful for high-risk screening of MPS 1, 2, 3, 4, and 6. We can detect really subtle alterations in the urine samples of these patients compared to controls. And we can monitor ERT. We found no interfering compounds at the precise retention time and masses that we're looking at. And as I mentioned, mass spectrometry is high resolution and high sensitivity with high specificity, which is quite good. So this is my medical center and the Faculty of Medicine and Health Sciences in Sherbrooke. So there's also an Institute of Pharmacology, there's the Clinical Research Center, and we have medical students, nurses. So it's 7 kilometers outside of Sherbrooke. You can see a bit in the countryside. We have deer. And this is my team. I always like to thank Fabry patients and MPS patients because I think they are so dedicated in providing urine samples. Without them, we wouldn't be able to do these research projects. I also work with Jeff Medine on gene therapy for Fabry disease and my colleagues at Canadian Fabry Disease Initiative all over Canada. And then without support, financial support, it wouldn't be possible to do these research projects. So I do with Genzyme, Shio, Biomarin, Waters. Waters, I have a beautiful partnership with them for mass spectrometry. They are very expensive instruments, so it's quite nice to have a good partnership with them. And the Canadian Institute of Health, La Fondation du CHU, La Fondation des Étoiles. So everybody, working together. It's a beautiful synergy. I always say it's like a big puzzle. You have all these people helping my team, really dedicated people. And in the end, in the middle of that big puzzle, there's a word called patience. And that's what we want to do. We want to make a positive difference in the lives of others and of these patients. So I thank you.